One of the most generally perceivable physicists, Michio Kaku, has discussed his assessment of this problem. Kaku, known for his astonishing contributions to genuine scientific fields, has acknowledged that the James Webb Space Telescope, JWST, has observed 6 colossal structures that experts once thought impossible. These findings could potentially lead to new perspectives on how we interpret the universe. This is both mesmerizing and well worth paying attention to. Kaku, a significant figure in physics, a Japanese-American physicist, has built a legacy as an authority in both theoretical physics and quantum mechanics. Unlike some experts who are more moderate and skeptical, Kaku does not belong to that group. He has been open to the groundbreaking discoveries of the JWST mission. We are fortunate that this esteemed scientist has decided to break his silence and address what can no longer be denied. His excitement and the essentially comprehensive tone of his remarks on the JWST findings are clear. He suggests that the revelations themselves have played a role in increasing his interest. We should investigate the consequences of Michio Kaku's acknowledgement of these 6 massive galaxies. Kaku, who has consistently had the ability to think about new theories, values scientific exploration, just as Einstein's theory of relativity and Newton's laws of motion shaped our understanding of physics. He realizes that the new telescope could essentially redefine our knowledge of the cosmos. However, many of his colleagues in the scientific community have struggled to accept this perspective. This has caused concern among both supporters and experts in quantum mechanics. Despite the controversy, Kaku finds the situation amusing. The JWST has discovered 6 mysterious, gigantic galaxies that date back to the very beginning of the universe. Each of these galaxies contains more stars than our own, despite forming just a short time after the universe's emergence. Cosmologists have named these extraordinary systems universe breakers because their existence challenges our current understanding of the cosmos. Something no longer aligns with the Big Bang theory. According to this theory, the universe was a chaotic place after its initial expansion. It took hundreds of millions of years for solid objects to form and even longer for these objects to gain enough density to illuminate. The formation of galaxies and other complex structures was expected to happen much later. Yet, some of the discovered galaxies are larger than the Milky Way, and their immense brightness suggests they were forming thousands of new stars per year, while our own galaxy forms far fewer. The precise timing of the universe's formation remains under debate, and researchers have struggled to pinpoint it accurately. Previous theories suggested that initially, the universe only contained single stars or small clusters of stars, which gradually merged to form dwarf galaxies that eventually grew through mergers and evolution. According to these ideas, highly advanced and massive galaxies should not have existed so early in the universe's timeline. This raises the question: is the universe actually older than we previously believed? Did large-scale, complex structures emerge much earlier than expected? This situation presents a challenge for mainstream science, which continues to wrestle with this unexpected model. Some areas of physics have outright dismissed the JWST's revelations, arguing that there may be errors in the age estimations. Kaku, aware of this controversy, has responded by pointing out that there have been many instances in history where outdated theories persisted simply because certain experts were unwilling to accept new evidence. Many of these theories were eventually proven incorrect when central evaluations exposed their flaws. Fundamental progress in science, especially in physics, relies on experimental validation and maintaining rigorous assessments. On Earth, we still lack complete knowledge of the actual origins of the universe. The Big Bang theory, first proposed in 1927, was based on observations of the universe's expansion. Scientists concluded that the universe began from a single point and has been expanding ever since. At the time, it was difficult for researchers to imagine a universe with both a beginning and an end. The idea that the universe had existed eternally and was infinite in time was deeply ingrained. Even today, scientists continue to face challenges in fully understanding this concept. However, it is crucial to reconsider these possibilities. The latest discoveries do not align with long-held theories about the universe's formation. Science has repeatedly shown that reassessment and openness are critical components of the scientific method. Just as Einstein once believed the universe was static, only to later be proven wrong, we must be prepared to revise our understanding based on new evidence. Today, researchers must confront uncomfortable discoveries and recognize that theories are not absolute truths until they are rigorously tested and confirmed by indisputable observations. The Big Bang theory gained traction because of observations showing that galaxies are moving away from one another, with their speed of recession proportional to their distance. This observation, known as Hubble's law, provided evidence for an expanding universe. Additional evidence, such as the cosmic microwave background radiation, the redshift of distant galaxies, and other cosmic patterns, has long supported the theory. However, it is important to remember that even widely accepted theories must be challenged when new data emerges. Despite the strength of the Big Bang theory, the James Webb Space Telescope, JWST, findings suggest that our understanding of the early universe may be incomplete. These 6 massive galaxies, existing far earlier than previously thought possible, challenge fundamental assumptions about the timeline of cosmic evolution. For decades, scientists believed that the first galaxies took hundreds of millions of years to form. The universe, after the Big Bang, was thought to be a chaotic place, filled with high-energy particles and radiation. Only after hundreds of millions of years did the first atoms come together to form small stars and galaxies. However, the JWST's discoveries suggest that massive galaxies, with fully developed star populations, existed much sooner than expected. If these findings hold, there are 2 major possibilities. 1. The universe is older than we think. If these galaxies are as old as they appear, then our cosmic age estimations may be incorrect. The current estimate of 13.8 billion years for the universe's age might need revision. 2. Galaxies formed much faster than expected. If the universe is indeed 13.8 billion years old, then galaxies must have formed at a much more rapid pace than our models predict. This would require an entirely new understanding of early cosmic structure formation. This revelation has sparked intense debate among physicists and cosmologists. Many traditionalists argue that the age estimations might be flawed, suggesting that these massive galaxies could be closer than they appear due to distortions in light measurements. However, others, including Michio Kaku, are open to the idea that these discoveries signal a paradigm shift in our understanding of the cosmos. The role of dark matter and dark energy. Another intriguing possibility is that these early galaxies formed due to unknown cosmic forces, such as dark matter and dark energy. Scientists estimate that 85% of the universe's mass is made up of dark matter, an invisible substance that shapes galaxies. Additionally, dark energy, the mysterious force causing the universe's expansion, remains one of the greatest scientific mysteries. Kaku has previously speculated that if the laws of physics do not align with observations, we must consider new physics, including the possibility that dark matter and dark energy played a much greater role in shaping the early universe than we currently understand. The future of cosmology. With the JWST continuing to deliver groundbreaking data, the scientific community must now confront a critical challenge. Do we revise our models of galaxy formation, or do we reconsider the fundamental assumptions of the Big Bang theory? This debate will likely continue for years as new data emerges. Regardless of the outcome, one thing is certain: our understanding of the universe is undergoing a profound transformation. Kaku, who has always been open to revolutionary ideas, believes that these discoveries are just the beginning. The JWST may ultimately rewrite the story of the universe's origins, just as Einstein's theory of relativity reshaped our understanding of space and time. As Kaku states, the universe is not only stranger than we imagine, it is stranger than we can imagine. People once thought the Earth was spherical and that the sun rotated around us. They also had similar types of evidence to support their fears until events or advances in technology gave a clearer picture. As of now, we are seeing a similar circumstance. Researchers anticipated the JWST to validate instincts about the Big Bang. Instead, they've discovered 6 systems that seem to be too big for their age. This reminds us that science is continuously changing, and experts must remain open to new discoveries and reassess existing hypotheses supported by evidence. Researchers employ redshift as a tool to determine specific measurements. The study of redshift in the universe, also referred to as the Doppler effect, explains the color shift in light as the light source and the observer move relative to one another. To understand this, imagine watching a car coming toward you. As it draws closer, you hear the motor getting louder. But once the car moves away from you or passes by, the sound changes. This is because sound waves change as the vehicle moves. The same is true for light. When a light source, like a distant star, moves toward us, the light shifts in the direction of the blue end of the spectrum. Alternatively, when the light source moves away, the light shifts toward the red end. Physicists who study redshift have converted redshift values into speeds and distances for surveying the universe. However, it is important to note that small errors in these computations could have significant implications. The estimation techniques used in the past are now under review, and the results researchers arrive at concerning the most recent discoveries of our universe are exciting. It is essential to examine whether these outcomes are genuine, based on redshift mistakes, or whether some researchers are simply denying the facts. This question necessitates careful examination and evaluation of the data and techniques used in the study. As scientific inquiry advances, discoveries made by instruments like the James Webb Space Telescope often challenge our assumptions about the universe. The ongoing discovery of 6 massive galaxies tracing all the way back to the universe's beginning is one such example. These systems, which defy the standard theory of galaxy formation, raise fundamental questions about the timelines and processes involved in the development of large-scale structures. The James Webb Space Telescope, a replacement for the Hubble Space Telescope, is equipped with state-of-the-art technologies that allow it to peer further into space with striking clarity. Its ability to detect light from the farthest reaches of the universe gives cosmologists a window into the past, allowing them to study galaxies that formed billions of years ago. The discovery of these ancient and massive galaxies challenges existing models, which predicted that such large structures should have formed much later in the universe's history. The implications of these discoveries extend beyond cosmology and into the realm of fundamental physics, causing researchers to reconsider established theories about the early universe. These discoveries also highlight the importance of remaining open to revolutionary ideas and updating our understanding based on empirical evidence. Michio Kaku has emphasized the pivotal role of scientific validation in shaping our perspective of the universe, pointing out that theories must continually evolve to accommodate new data. The debate sparked by these revelations reflects the ever-changing nature of scientific inquiry. On one hand, some supporters argue that the discovery of early massive galaxies suggests a longer timeline for galaxy formation than initially believed. This viewpoint challenges the traditional view that galaxies evolve slowly over billions of years through mergers and the gradual development of smaller objects. On the other hand, skeptics caution against quickly dismissing established models based on limited observational data. They advocate for a more cautious approach, suggesting that discrepancies in data, errors in interpretation, or measurement issues could account for the shocking findings. Redshift, a phenomenon observed in the light emitted by distant galaxies, plays a critical role in these fundamental assessments. As galaxies move away from us, their light shifts toward longer wavelengths, a phenomenon known as redshift. By determining the amount of redshift in a galaxy's light spectrum, cosmologists can deduce its distance from Earth and its speed relative to us. This data provides key insights into the expansion of the universe and the dynamics of galaxies. The combination of redshift data and advanced telescope observations has led to remarkable advancements in our understanding of the universe. However, new findings, such as the 6 massive galaxies discovered by the James Webb Space Telescope, present challenges to the current understanding of cosmic evolution. As the scientific community continues to evaluate and refine models of galaxy formation, the ongoing dialogue between theory and observation highlights the potential for new data to reshape our understanding of the cosmos. These recent discoveries emphasize the need for continuous refinement in our understanding of cosmic evolution. If galaxies of such massive scale existed in the early universe, it suggests that our current models may be incomplete or require significant adjustments. Scientists must consider alternative explanations, such as new physics, revised estimates of star formation rates, or even the possibility that our understanding of redshift itself needs re-evaluation. One possible explanation for these unexpected findings is that early galaxies formed and evolved much faster than previously assumed. If this is the case, it would challenge the long-held belief that galaxies gradually assembled over billions of years through mergers and accretion. Instead, it may indicate that under the right conditions, large-scale structures could have emerged more rapidly, requiring a reassessment of the fundamental forces driving galaxy formation. Another consideration is the role of dark matter and dark energy. These two mysterious components of the universe remain poorly understood, yet they are believed to shape the structure and expansion of the cosmos. If the JWST's discoveries hint at anomalies in galactic formation, it might suggest that dark matter interacts differently than we assumed, or that dark energy played a different role in the early universe than current models predict. Additionally, the possibility that redshift measurements themselves may not be as reliable as previously believed cannot be ruled out. While redshift has been a cornerstone of cosmology, any errors or overlooked variables in the way we interpret these measurements could lead to miscalculations of distances and cosmic timelines. If so, it would have profound implications for our understanding of the age and size of the universe. The implications of these findings extend beyond astrophysics, impacting the broader field of fundamental physics. If large galaxies existed in the early universe, it could suggest the need for modifications to the standard model of particle physics or even the theory of general relativity. Scientists are now considering whether additional forces or undiscovered particles may have influenced the formation of these massive structures. As researchers continue to analyze data from the JWST, collaboration across different scientific disciplines becomes increasingly essential. Astrophysicists, theoretical physicists, and cosmologists must work together to either reconcile these findings with existing theories or develop new frameworks that better align with observational evidence. The ability to adapt and refine theories based on new data is a defining characteristic of scientific progress. Moreover, these discoveries remind us of the importance of skepticism and open-mindedness in science. While some may rush to embrace revolutionary interpretations, others urge caution, emphasizing the need for thorough verification and replication of results. A balanced approach, one that neither clings stubbornly to outdated models nor hastily discards established principles, is crucial in advancing our understanding of the universe. Looking ahead, future observations from the JWST, as well as other upcoming space telescopes and observational tools, will help clarify these mysteries. Whether these findings ultimately lead to a revision of cosmic history or reinforce existing models with slight adjustments, they represent a pivotal moment in our exploration of the universe. The nature of scientific inquiry is not about seeking absolute certainty but about continuously refining our understanding through observation, experimentation, and critical analysis. The discoveries made by the JWST serve as a powerful reminder that the cosmos still holds many secrets, waiting to be uncovered by the next generation of explorers.